Go.
Okay, so this is problem 6.26 from the homework. And it reads, a 10-kilogram crate is placed on a horizontal conveyor belt. Okay, so we'll start out with the given.
30 minutes. It says like 85
The given,
minutes.
so we know that the mass is 10 kilograms.
Should we get the
10 kilograms. And the materials are such that the coefficient of static is 0.5. So that's μs is equal to 0.5, and coefficient of kinetic is 0.3. Okay, so it's on a conveyor belt, so we can draw a picture. Draw a nice little picture here with a conveyor belt.
But like you could test if you get it right.
Okay, 10 kilograms. Alright, so that's our picture of the scenario. So now the first question says, it says draw a free body diagram showing all the forces on the crate if the conveyor belt runs at a constant speed. So that's A. So A, if it has a constant speed, so I'll draw the picture again and simplify. Yep. So if the conveyor belt is moving at a constant speed, so we have V. I'll put V con for V conveyor belt. It's moving at a constant speed. Say it's moving to the right constantly. So V con is constant. So if V con is constant, we want to draw a free body diagram for that. That means that if this is constant, this box, V box, I'll call it, should be 0.
Try to use my hands.
It's not gonna move, or it'll be the same as this. I'll do that. V box will be equal to V con. Because if it's moving that way constant, this box has no X forces that are acting on it, so it'll move with the conveyor belt. So the free body diagram for that should just look like this. Because we, as I said, I think 2 seconds ago or a minute ago, the forces in the X are equal to 0 because it's moving constant. And then also the forces in the Y are equal to 0. So we know that mg minus n, n minus mg is equal to 0. So normal is equal to mg, which is fg. That's the free body diagram for the first one. That's part A. Part B says draw a free body diagram showing all the forces on the crate and the conveyor belt speeding up. So that's basically just this. So
I hate math so much.
you have your
Math is
the
the
box,
It's
10
the
kilograms.
So the 4,
plus 1 and then the plus 2.
yeah.
Right, you have your box 10 kilograms. And in this case, you still have the forces, normal,
Extra year
and
is
then mg.
Yeah.
Alright, so in this case, V con is that way, but V con is not constant, as in this case. So if this is not constant, that means that there's an acceleration acting in this box. So
Isn't the 3 plus 2?
this is tricky because some people say, oh, if V con is that way, then the box should have a friction force that's pointing the opposite way. But the box has a friction force, but it's pointing the way of V con, and I'll explain why. So if we do a free body diagram, we'll have the normal force on the box, and then in this case the friction force is that way. The friction force is that way because when you have an object on top of an object that is in motion, so say if I'm on a treadmill and I'm stationary on the treadmill and I press the treadmill to start and the treadmill accelerates this way, but at a very fast speed or at some type of acceleration, then my body will react and tend to move this way. So like, I guess my feet will go forward with the treadmill and I'll go backward. So in this case, the same thing happens. So this part of the box moves this way, but then the box will tumble backward. And that's more rotationals, but that's later on. But yeah, it will tumble backward. So G box is that way, which means the friction force should be opposite of that, which is this way. So that'll be a free body diagram for that. And if we do this again, that is going to be,
Yeah, and they're here till like 10.
it's not going to get to 0 because it's a charge. Y should be equal to 0. And then the same, for the same reasons here. So these are equivalent.
You can even use a classroom.
Wait,
Yeah. As long as there's like they put a schedule, you know, like on the door, so they
Yeah,
don't.
like I mean, obviously, if there's
Those are equivalent. Okay, now C.
And if not, like even if
Um,
there's no brain, like
For C it says, what is the max acceleration? So,
you can always do what's the
another
library.
picture
Like,
again.
and we want to do it in like
That's a thick conveyor belt, but it's
I know
okay.
what you get out the way.
We have normal, mg from the center of mass, and it's still gonna have that coefficient of friction, which was in this problem. But instead of it being,
because you know how there's like a round table
I believe this one is kinetic, so I'll put a K there. This one is static,
and drinks if the machine.
right? So when we do the free body diagram, normal, mg, ff static. So we're gonna do this process again. So the addition of forces in the x is equal to friction force static. And then this is literally the same again. Now, so in this case, we can say that, so in case B, we know that the F net is gonna equal to friction force K. And then in this case, the F net is equal to the, I don't know why this is here. I mean, force is a vector, so yeah. So friction force S, as forces are vectors. So, we know F net equals that, but we also know that it equals to MA. So if it equals MA, the friction force equation, I like to call it the Fuffin equation.
I want to stick to this part, but I can't do that.
Fuffin, you know this,
Not like the number.
and this is static, so that'll be S, so Fuffin. This is the normal, this is the coefficient of friction from over here, which is the 0.5. So we have 0.5, and then Fn. Fn is equal to, just like in this case, Fn or n is equal to Fg. So that would be Fg, which is equal to mg. So we can just substitute mg for the normal force here. So the mass, I can just put mg. I'll put mg. Well, actually, no, I'll just keep uk. I like to use numbers at the end. That's mu s mg is equal to m a, and I'll put a max because that's what they want. So then, these will cancel, and you're left with mu s times g is equal to a max. And then now you plug in, so you have 0.5 times 9.81 meters per second squared equals A max, and then A max is going to be equal to, I think, what is that, 4.9 meters per second squared. If I wanted to do a fast computational way, since this is 9.81, you can round that up to 10, and then 10 times 0.5 is just 5. So you can put A max is approximately 5 meters per second squared. So those are the answers. And I guess one more thing to point out is that the only reason why this rings true is because we're on a flat horizontal surface. If we were on an incline per se like this, I guess, and then the box was here, and there was a conveyor belt or something, then this is the normal force, but this is mg. So the component of mg will equal the normal force instead of actually being mg. So in this case, we can get away with saying mg is equal to m, but if it's on an incline, you can't get away with that. So that's the whole 6.26 problem.